All right, let's look how we do this problem that we've given you. So first thing we're going to do is let's draw a picture. There are two charges. We have a negative 10 microcoulomb charge and a positive 27 microcoulomb charge. They are separated by 10 millimeters. And we want to know the force between them. So, what do? Looks like we're going to use Coulomb's law. If you remember Coulomb's law, that the force of the electric field is K, Q1, Q2 over R squared. So, that's our equation. So, remember, K was Coulomb's constant. That is 9 times 10 to the 9th newtons times meter squared over Coulomb squared. Q1 is one of the charges, it doesn't matter. Q1, let's pick the one on the left, that's negative 10 microcoulombs. Q2 then is positive 27 microcoulombs. And R is 10 millimeters. Now, something to remember is with our positive and negative in charges. In forces, remember, that meant a direction. But in our charges, that's a kind of charge. So it has nothing to do with direction. So what we're actually just going to do is drop them. Because it has nothing to do with the direction of the force, that positive and negative. It's a type of charge. So we just have 10 microcoulombs and 27 microcoulombs, and then we'll look at the end to see what direction that the force is acting. Okay, so let's put our information in our formula. So we have the force of the electric field equals K. That's 9 times 10 to the 9th newtons times meter squared over Coulomb squared times Q1, 10 microcoulombs, times Q2, 27 microcoulombs, all over our R, 10 millimeters squared. So now if we notice that our units on our Coulomb's constant K are newtons, meters, and coulombs, and yet our charge is in microcoulombs and our distance is in millimeters. So we're going to have to do, we need to switch those out of there. Those are just our metric prefixes, so we can remove them. So if we have 10 microcoulombs, remember micro is 10 to the negative 6. So that's 10 times 10 to the negative 6th coulombs. 27 microcoulombs is going to be 27 times 10 to the negative 6. Remember, this is our prefix, so we can just pull it off. Our 10 millimeters, remember to go from millimeters to meters, it's 3 decimal places. So 1, 2, 3. So that's 0.010 meters. So now we've got our units all correct, so we can put it back in our formula. So we say that the force of the electric field is Coulomb's constant, 9 times 10 to the 9th newtons times meters squared over Coulomb squared, times 10 times 10 to the negative 6th coulombs, times 27 times 10 to the negative 6th coulombs. And if you notice, it doesn't matter whether we use a capital C or a lowercase c. I kind of switch back and forth, so it doesn't matter in these problems or in any of our problems. Coulombs can be capital or lowercase. So then that's 0.01. I'm just going to drop that 0 meters squared. Okay, so if we run it through our calculators, if we do our top first, multiply all three of those numbers together, we get 2.43. On the bottom, if we square 0.01, we get 1 times 10 to the negative fourth. Now, that unit we can easily see, that's meters squared. But what about on top? Well, we have a coulomb squared there and a coulomb there. So don't those all cancel out of there? So that means we have newtons times meters squared on top. So now when we divide those two, you can see the meters will leave us. And so our force of the electric field is going to be 2,4,3,0,0 newtons. So there's our force between those two charges that are 10 millimeters apart.